Kathy Sem, Product Manager at JEOL USA. So today I will be presenting on the analysis of lithium-ion batteries using scanning electron microscopes with a focus on JEOL's advancements in next-generation X-ray analysis techniques for lithium detection. So JEOL is a world leader in the manufacture of scientific equipment, covering a broad range of industries from medical biochemistry analyzers to industrial equipment to analytical instruments. JEOL makes a variety of products that are relevant to battery characterization, including TEM for nano and atomic scale observation, SEM, EPMA, and Auger microscopes for surface morphology at the micro to nano scales, EDXRF, EDS, WDS, and SXES for elemental analyses, both qualitative and quantitative. SXES can also provide insights into chemical state. FibSem and cross-section polishing, which are used for sample preparation. NMR for structural analysis and lithium diffusion, and mass spec for chemical analysis and evolved gas analysis. So today's presentation will focus on JEOL's advanced solutions for analyzing lithium-ion batteries using SEMs with our innovative X-ray detectors. So I'll begin by introducing the advantages of JEOL products for lithium-ion battery preparation and workflow, like the integration of our EDS detectors within our SEM software interface for real-time live analysis, as well as the SEM automation protocols that can enhance efficiency and reproducibility in battery research. And I will address how to minimize sample damage during preparation with a focus on JEOL's cross-section polisher, a critical tool for preparing lithium-ion battery cross-sections for high-resolution imaging and analysis. The core of the presentation will explore a collection of data taken on various battery materials, and especially focusing on lithium detection in different alloys and compounds using two of JEOL's state-of-the-art X-ray detectors on our ultra-high-resolution SEM platforms, the Gather-X Windowless EDS detector and the Soft X-ray Emission Spectrometer. So these detectors offer exceptional sensitivity for light elements such as lithium and fluorine, and when used together, enable comprehensive chemical and structural characterization of a wide range of materials. The presentation will conclude with a case study showcasing how both detectors were used in tandem to fully characterize a silicon anode in an all-solid-state lithium-ion battery in situ across charge-discharge cycles, highlighting the power of JEOL's integrated solutions. To begin, I'd like to mention that JEOL has a comprehensive lineup of SEMs to cover all major applications, from the macro to the nanoscale. Easy benchtop systems all the way up to ultra-high resolution field emission instruments all have their role to play in battery characterization. Operating any of our SEMs has never been simpler. There's an easy workflow, and one can go from loading the sample and navigating to the area of interest, to clear, sharp images in live analysis, to easy report creation in a matter of minutes. Here's just a quick overview of some battery data that was acquired with JEOL's benchtop system. So it's incredibly easy to use, it comes at a great price point, and can be quite useful for the characterization of battery materials. In the top image, we show an anode material acquired using the secondary electron detector at low voltage to highlight the surface structure. Below it is a backscattered electron image from a cross-section of a cathode, highlighting the composition contrast between the cathode material and the current collector. And our benchtop system can even be equipped with JEOL's EDS detector for elemental analysis, and the colored image on the right shows an overlay of the X-ray elemental maps for this cathode showing the elemental distribution. And any JEOL EDS detector on any current JEOL SEM also allows for live EDS spectrum analysis while imaging. Here you can see a top-down image of a cathode material and its associated live spectra. JEOL prides itself on its no-code automation features, meaning ways to automatically acquire images in EDS analysis without scripting. One of these features, which comes standard with any current JEOL SEM, is montage. This function automates the acquisition of images and EDS maps over large areas and stitches the images to form one large composite image. And both the individual images and maps are also saved. This example shows a 4x4 montage of that cathode material taken with our ultra-high resolution SEM. The complete montage, including backscattered and secondary electron imaging along with the EDS map analysis, was acquired in approximately 25 minutes. Shown here is the EDS map analysis data for just one of the montaged frames. So a single pass at 512 by 384 pixel resolution was completed in just 40 seconds. So despite the short acquisition time, the signal quality and detail are excellent because we used 5 nanoamps of beam current. In total, 16 frames of this quality were acquired automatically and unattended during the montage process. JEOL's cross-section polisher plays a vital role in producing high-quality lithium-ion battery cross-sections for high-resolution imaging and analysis. One of the key advantages of using JEOL's cross-section polisher, or CP, is its ability to eliminate artifacts commonly introduced by traditional mechanical preparation methods. The CP enables the creation of pristine cross-sections in challenging sample types and produces surfaces with minimal mechanical strain and distortion, making it particularly well suited for surface-sensitive analytical applications. This example demonstrates how JEOL's cross-section polisher can significantly reduce mechanical damage in cross-sectional imaging of battery samples. The sample shown is an anode material prior to charging, where air isolation and cooling are not required. On the left, a fractured surface reveals irregularities in large voids caused by mechanical stress. In contrast, the CP prepared cross-section on the right exhibits a much smoother surface. The copper grain structure is visible, and the interface between the copper and graphite can also be clearly observed. The next example highlights the benefits of using cryogenic temperatures when cross-section polishing to mitigate thermal damage. This sample, which is an anode material post-charging, develops a thermally unstable film on the graphite of the negative electrode, necessitating cooling during preparation. So the room temperature preparation on the left shows significant deformation and void formation, likely due to the heat generated during the milling process. In contrast, the cryogenically cooled sample on the right displays a uniform graphite structure with a smooth, undistorted cross-section. Also, we examined the impact of atmospheric exposure on a cross-sectioned anode material after charging. So the SEM image on the right reveals a break in the interface between the copper and graphite, along with changes in the thickness of the graphite layer. At higher magnification, we see increased gap sizes between the graphite particles and signs of oxidation and surface deposits. So when comparing optimally prepared cross-sections of the same anode material before and after charging, only subtle differences in the graphite layer thickness are observed, thanks to the artifact-free preparation enabled by JEOL's cross-section polisher. Okay, so for the remainder of the talk, I'll be showing data gathered using our advanced JEOL X-ray detectors on the ultra-high resolution field emission SEM. I'll start by showing data from our Gather-X Windowless EDS detector. This detector is 100 millimeters squared and has a racetrack design. It can be used at any kV, but is especially sensitive for detecting low energy X-rays down to 50 eV. This spectrum on the bottom right is comparing the sensitivity of the Gather-X below 1 kV to a comparatively sized standard EDS detector at only 100 picoamps. You'll notice not only significantly more signal, but also that we can resolve lower energy X-rays, including the aluminum L line, shown here, which is absorbed by the window in a standard EDS. And what that sensitivity translates into is not only the ability to detect low energy X-rays, including lithium, but also the ability to analyze samples at much lower probe currents and lower accelerating voltages. So why would we want to analyze lithium-ion batteries at low kV? Here's a quick example of NMC particles from a battery cathode, imaged at accelerating voltages of 7 kV, 3 kV, and 1.5 kV. At 7 kV, the high beam energy penetrates the binder material, making it barely visible. Improved contrast and resolution of the binder are observed at 3 kV, with further enhancement at 1.5 kV, allowing for clearer visualization of the binder structure. Since X-rays penetrate even deeper than backscattered electrons, we would expect to see this same trend in the EDS data as well. The signal depth at 7 kV is shown for a carbon sample in the top right. This signal depth feature is standard on the JEOL SEM software for a quick look at how deep the beam will penetrate into a sample for EDS analysis. This depth will change based on both the KV and the material, which can be selected in the software. Here you can see the corresponding EDS analysis of the NMC at 7 kV, and then at 3 kV, and then at 1.5 kV. So now, if we take a closer look at the carbon maps from these 3 studies, along with Monte Carlo simulations, the depth of penetration using that standard signal depth feature for each accelerating voltage is located on the top left of each simulation. So it's easy to see why we get this improvement in surface sensitivity and resolution of the binder material by reducing the accelerating voltage, since what we're doing is we're reducing the depth of penetration of the beam from 800 nanometers into the sample down to about 60 nanometers. So at the lower KVs, we'll not be picking up much of the sample below the binder itself. So with intelligent features like the signal depth, you never need to guess which voltage you should be using for EDS analysis. And to take it one step further, we can leverage our new neo-action function on the IT810 series, ultra-high resolution microscopes, to automatically acquire images and EDS maps like this at several conditions, using the auto functions to focus and align at each new region of interest or condition without any user intervention. So this works very well with the auto functions, even at high magnifications, because a combination of drift correction and beam shift is utilized to counteract the stage reproducibility for fields of view smaller than tens of microns. You can also save and then recall any recipes for routine analyses on different samples. The increased sensitivity of our Gather-X detector enables higher throughput analysis, allowing more comprehensive data sets like this to be collected without sacrificing productivity. And here we look at low energy analysis on a NMC cathode material in order to see the high spatial resolution of fluorine in the material. The data is taken at 1.5 kV, and we can use 5 nanoamps of current for quicker analysis while still maintaining a small probe size. The high counts improve the peak separation accuracy and enables us to acquire more clear and accurate distribution of fluorine. One thing you will note here is that we do not see lithium in this sample. This is because when lithium is bonded to oxygen, it generates very, very few X-rays. So we will generally not be able to detect it with EDS, even with a windowless EDS detector. But we should be able to detect metallic lithium. However, we will need to use air-isolated procedures to prepare it in order to stop the lithium metal from oxidizing in air. This video will show JEOL's elegant solution for air-isolated applications, which can be completed on top-down samples or in one workflow, including JEOL's cross-section polisher. A sample can be prepared in the glove box and capped. Then the sample can be brought to the cross-section polisher, evacuated, and then uncapped and cross-sectioned. When the cross-section is complete, it can be recapped and brought directly to a JEOL SEM. The sample can be placed into the airlock and evacuated, and then uncapped before loading the sample into the chamber. Here's an example of lithium metal which has been cross-sectioned. And here are the spectra taken at a position near to the surface and at the inner area of the cross-section. You can see the very clear lithium peak in both spectra, and that the near surface area shows more oxygen and less lithium. And here's an example of a silicon anode from an all-solid-state lithium-ion battery material, which adopts a solid electrolyte between the cathode and anode. As you can see, the Gather-X can not only detect the lithium, but it can also deconvolute the lithium K and silicon L lines, which are only 36 eV apart. Here you can see mapping with very good separation between the lithium and silicon areas, even with that strong overlap in peaks. And here's an example of a few sulfide solid electrolyte materials, which are also used in all solid state batteries. We can see that Gather-X can detect lithium in these compounds, as well as the phosphorus and sulfur characteristic L X-ray energies with high sensitivity. And here we can see the spectra for a selection of other lithium compounds related to battery materials. The top four, including lithium metal, are easily detectable with the Gather-X, and one of those is an alloy with silicon. You can see here that the peaks are overlapping, but can be distinguished with deconvolution. Now, there are, of course, detection limits. Lithium is in general not going to produce substantial X-rays if it's within an oxide material, as you can see in the bottom two curves where a lithium peak is undetectable. But even with alloys, if there are elements mixed with the lithium that have even closer overlapping peaks than silicon, and also depending on the percentage of lithium, lithium might be hard to detect with the windowless EDS detector because of the energy resolution of this technique. So here, the center three materials shown, which are alloys with magnesium, aluminum, or bromine, all have very small peak energy separations with lithium. In those materials, the Gather-X would not be the most ideal method for lithium detection. So in fact, JEOL does offer a solution for lithium detection in those types of materials, which is our Soft X-ray Emission Spectrometer, which I'll discuss next. The SXES is available on both our ultra high resolution field emission SEMs and our EPMAs. Here's a diagram of how it works. It provides parallel detection of low energy X-rays using a focusing mirror, a high energy resolution diffraction grating, and a CCD camera to acquire a spectrum that is similar to an EDS spectrum. This unique design offers the best spectral resolution of soft X-rays available on any commercial SEM or EPMA. It can not only detect light elements, including lithium, but can even detect trace amounts of these light elements in the 100 ppm range. Here you can see the resolution in the spectra between EDS and SXES on the left, showing an L-line spectra comparison in stainless steel. And on the right, you can see the comparison of the resolution of the carbon K emission spectra between EDS, WDS, and SXES, where SXES spectra is blue in both graphs. And if we return to that Gather-X EDS spectrum that I showed earlier of lithium and silicon in an all-solid state lithium-ion battery, where we needed to rely on peak deconvolution to separate the lithium K and silicon L lines, the SXES is fully able to resolve those peaks, making it a powerful technique in battery research, for example, for both detecting lithium and for analyzing the chemical state of the silicon anode. So how do we actually analyze the chemical state with SXES? This has to do with how the signals differ between this technique and with EDS or WDS. So consider looking at an energy band diagram shown here on the left. For EDS or WDS, we're looking at the transition of characteristic X-rays emitted from electrons moving from, say, the L to the K shell. The shape of that peak will be less affected by the chemical state, but the spectral intensity will change in proportion to the concentration. So that allows for elemental analysis and quantification. The ultra-low energy X-ray lines detected on the SXES are more likely to contain chemical state information, even for the higher atomic elements. While the K transitions are generally not from the valence bands, these ultra-low energy transitions from the M or L shells do frequently involve transitions from the valence electrons, shown here. So thus, these signals can have valence band information, allowing one to determine the chemical bonding state of materials based on the peak's position and its shape. So what this novel technology translates to, besides detection of low energy elements like lithium, is the ability to assess the chemical state information, such as shown in the graph on the right, where the asymmetry and peak width in the carbon K line directly relate to the p symmetry of the carbon valence bands. So with SXES, we can tell the difference between graphite and diamond, even though they are both completely made of carbon, something that's not possible with EDS or WDS. We offer 3 different SXES versions that each have a different available energy range, shown here. The versions, along with some common research applications, are presented in this diagram. The version I'll discuss here is the one most applicable to battery research, which is the VUV option, which extends the available energy range to the vacuum ultraviolet region. This is specialized for lithium detection and lithium compound analysis, and has even been used in some cases to detect lithium in compounds where oxygen is present. So remember this graph that showed the detection limits of the Gather-X in relation to battery materials where we could not separate out the lithium peak with the magnesium, aluminum, or bromine? So here are the spectra from these same samples, now also taken with this VUV version of the SXES. The x-axis is more zoomed in. It's only showing half of the x-axis in the Gather-X data. But for these samples, in each of those alloys where the peaks were too overlapped, with the SXES detector, the lithium can now easily be detected, and the peaks are even completely separated, even in the case of magnesium, where the peak separation is only around 5 eV. So note that even using this new SXES grading, which is specialized for lithium compounds, this experiment did not detect lithium in the two bottom battery materials that involve lithium and oxygen. However, even though the intensity is very weak, it is still possible to detect lithium in certain oxide compounds with the newest version of SXES. Here we can see the spectra for lithium and a lithium corrosion layer on an electrode. The ratio of intensities here is 60:1, which means the detection will require much longer measurement times for oxide compounds than for lithium in any sort of metallic form. The intensity of lithium is so low, again, because the outer shell electrons that are shared and bonded with oxygen, so that means very few lithium X-rays are actually produced. So this is just physics. And here you can see spectra from a selection of other lithium oxide materials. Since the emission is very weak, high probe currents and long measurement times of 1 hour per spectra were used. So even though the signal is weak, we can detect a slight lithium peak in these materials. Now, I also showed lithium cobalt oxide before and said it was not possible to see a couple slides ago. But in this case, it's a different sample of this material, and the measurement time is much longer with higher currents and lower kV. And here we can see SXES spectra for a few other lithium compounds. It's possible to detect lithium in lithium carbonate, lithium tantalate, as well as lithium manganese oxide powder, shown here. Also, lithium is possible to detect in some halides like lithium bromide, lithium chloride, and lithium fluoride. And we're currently conducting more studies to see which lithium compounds allow for lithium detection using this method. Since lithium has such a low energy X-ray line and it's easily absorbed by other elements before it can escape the sample, potential customers should always be on the safe side and send us samples to test to make sure that the SXES will be able to answer your research questions with your type of samples. I also want to mention that the SXES will not replace a standard EDS or WDS. Because of the energy range available, the entire range of characteristic energies cannot be reached with it. So it can only be used for certain elements and transitions. The SXES is used more for determining chemical state or trace element detection. And if you are interested in quantification, EDS or WDS is still best, since quantification with the SXES will require a calibration curve. So it's best to use the SXES to complement an EDS or WDS system. In fact, it's also possible to install both the SXES and the Gather-X Windowless EDS detector together on JEOL's ultra-high resolution SEMs. These techniques can be very complementary, which is shown in this chart. Generally, one would use the Gather-X for your nanoscale analysis, lithium detection in metals, for quantification, or to quickly map an area. And then one could analyze the chemical states of the different elements found in those areas with SXES, or detect light elements like lithium in compounds or in trace amounts. And lastly, what I want to do is show an experiment using both the Gather-X and the SXES on JEOL's ultra-high resolution SEM. So this is an example of an in situ operando experiment with a charge-discharge system in the SEM. So in order to perform this experiment, we designed a pressure stack holder for an all-solid-state lithium-ion battery. It was designed for analyzing silicon negative electrodes, which typically have high expansion rates. So this holder allows preparation and observation while maintaining a confining pressure and is compatible with both our cross-section polisher and our air isolation workflow. So keeping the sample in the same pressure stack holder throughout the process ensures the sample integrity. In this experiment, NMC was used as the positive electrode, and there was a sulfide electrolyte. The sample was punched into a 5 mm square using the Nagomi punching jig, transferred to the cooling cross-section polisher, and the cross-section was milled at -120 degrees. Then the sample is brought back into the glove box, and the base of the sample holder is replaced with this specialized holder base that has terminals that connects directly into the stage side of the SEM, which is in turn connected to a battery cycler. So here's a photo of this setup and the specific settings that are being used for the milling, the observation, the mapping, the SXES, and the charging and discharging. Now, using our Gather-X EDS detector, X-ray maps were collected during the charging and the discharging. I wanted to mention first that JEOL's EDS software on any of our SEMs not only collects EDS maps, but also an image with each frame. So we have what's called playback analysis function to view the full time domain of our experiment. The data can be replayed after measurement, and also data can be extracted from any portion of the time domain. So this is very effective for observation of systems with temporal changes, such as this study. Okay, so this is how the silicon negative electrode changes during charging of an all solid state battery. So the charging in this slide is the charging rate is from 0% to 10%, and the actual elapsed time is 30 minutes. The left image is a backscattered electron image, and the right is an EDS map using the Gather-X detector with lithium K in yellow and silicon L in light blue. In addition to the gradual expansion of silicon particles as a result of charging, from the EDS maps, we were able to observe how lithium gradually intercalated into a silicon particle at the interface between the silicon negative electrode and the solid electrolyte. Furthermore, from the fact that lithium was selectively inserted into some of the silicon particles that are in contact with the interface, it was revealed that there are certain silicon particles that are more easily alloyed with lithium. Next, we focused on silicon particles with little change in the backscattered electron image contrast in EDS map during the charging from 0 to 10%, and conducted further charging and discharging studies to target them for SXES analysis. So before charging, the silicon L peak is characteristic of crystalline silicon, and we don't see any lithium. At 10%, the peak shape of silicon L changes slightly, and a very small lithium peak is visible. At 20%, the lithium peak intensity increases, and there's a further change in the silicon L peak shape. This is corroborated by the change in contrast in the BSE image and the observation of lithium intercalation from the EDS map. At 40%, the silicon L peak shape has changed dramatically, and the lithium K intensity has increased even further. Also, the lithium peak position shifts to 53.4 eV, suggesting that the lithium is alloying in the silicon particle. And finally, looking at a fully discharged condition, the lithium K peak intensity becomes lower, and the silicon L peak shape is similar to that of amorphous silicon, indicating that the chemical state of the silicon particle has changed due to the lithium insertion and extraction. It can be assumed that some lithium remains in the silicon particles. And the silicon layer that became amorphous in the first cycle remains amorphous and was still able to absorb lithium during the charging and repeatedly form lithium-silicon alloys after the second cycle. So starting with the second cycle, the silicon remains amorphous throughout both charging and discharging. In this experiment, we went through 14 charge-discharge cycles. In this graph, we're showing the data for the first, the second, and the 14th cycle for both charged and discharged. And looking at the lithium peak in the data, we can see that the peak intensity of the lithium decreases with the lithium-silicon alloying, reducing significantly by the 14th cycle. So in summary, JEOL offers a comprehensive suite of solutions for the analysis of lithium-ion battery materials. The Gather-X Windowless EDS detector delivers a highly intuitive user experience and offers enhanced sensitivity at low accelerating voltages while also supporting high voltage analysis. Its high spatial resolution enables precise elemental mapping of sub 20 nanometer particles and thin surface layers. The Soft X-ray Emission Spectrometer provides detailed chemical state analysis and is capable of detecting light elements such as lithium and boron at concentrations as low as 100 to 200 ppm. JEOL's integrated SEM technologies, including the IT810 series, cross-section polisher, Gather-X, and SXES, offer a powerful and versatile platform for the advanced characterization of lithium-ion battery materials. These tools enable high-resolution imaging, precise elemental mapping, and detailed chemical state analysis, all while minimizing the sample damage and maximizing the analytical efficiency. So together, they provide researchers with the capabilities needed to push the boundaries of battery innovation and material science. I'd like to thank my colleagues at JEOL Limited in Japan and JEOL France for providing some of the data that was in this presentation. And thank you very much for listening.